Hello, welcome to another module in this massive open online course. So currently we are looking at OFDM or orthogonal frequency division multiplexing, and we are trying to understand the mechanism of OFDM. And we also said OFDM is a modern wireless technology which can efficiently overcome inter-symbol interference, correct. So what we are looking at currently is you are looking at estimation in the context of OFDM, where OFDM stands for orthogonal frequency division multiplexing, correct. And we said OFDM can be used to efficiently overcome ISI or basically inter-symbol interference. For instance, we have our, and we have seen this many times before, yk equals h0 xk plus h1 xk minus 1 plus vk. This is our 2-tap ISI channel. So this is basically the model for your 2-tap ISI channel, where the taps are H0 and H1. Xk is the current symbol, xk minus 1 is the previous symbol, all right. So there is inter-symbol interference of the previous symbol xk minus 1 on the current symbol, and we said OFDM can be explained as follows. So OXDM, we have, let us consider a typical OFDM system with 4 subcarriers, that is we have the symbol x0, capital X0, capital X1, capital X2, capital X3. These are the n symbols, that is these are n equal to 4 symbols. These are loaded onto n equal to 4 subcarriers, and the meaning of this is basically, the meaning of this term loaded is basically we perform n equal to 4 point IDFT or IFFT, the inverse fast Fourier transform, which is basically the inverse fast Fourier transform. One can perform IDFT or equivalently IFFT. IFFT is nothing but the same as the IDFT, but it is an efficient, it is a fast algorithm to perform IDFT, that is the inverse fast Fourier transform. Okay. So now therefore the samples from this, what you have is from this capital X0, X1, X2, X3, we generate what are known as the samples, that is by IFT, that is the samples X0, X1, X2, X3, and these are generated by the, these are the n equal to 4 samples and these are generated by the IDFT as, and all of you must be familiar with IDFT, that is basically we have x of k equals 1 over n summation L equal to 0 to n minus 1 capital X of L, that is the symbols loaded onto the subcarriers, e to the power of j 2 pi k L by n, and now I am going to substitute n equal to 4. So, this gives me basically 1 over 4 summation L equal to 0 to 3 capital XL e raised to j 2 pi k L by 4, which is equal to, therefore, your X L is basically equal to 1 over 4 summation L equal to 0 to 3 XL e raised to j pi by 2 k L, all right. So, this is basically the sample. So, these are the symbols loaded onto the subcarrier, that is your BPSK, QPSK symbols, etc., and these are the samples. And now we said we are not going to, we want to transmit the samples, but we do not transmit the samples as it is. We have a small modification before transmission of these samples over the channel. We add the cyclic prefix, that is, we take a few symbols from the tail of the block and prefix them at the head of the block. Since we are cycling symbols from the end towards the head, this is known as a cyclic, this is a cyclic operation, and also since we are prefixing them, this is known as cyclic prefix. So, in the second step, what we do is you have your samples x0, x1, x2, x3, and what I have is now again I am basically cycling the samples from the end towards the beginning. This is known as a cyclic prefix. This is denoted by the term Cp. Okay. And now this block with Cp added, this is transmitted over the channel. Remember, our channel is our frequency selective channel, that is Yk equals H0 Xk plus H1 Xk minus 1 plus Vk. Now, when I transmit the samples, your cyclic Cp added samples, that is X3, X0, X1, X2, X3. Now, observe the output corresponding to X0. Output corresponding to X0 is Y0 equals H0 times X0 plus H1 times the previous symbol, but the previous symbol to X0 is X3. This is the previous symbol because of the addition of cyclic prefix. This is your previous symbol to X0 because of the addition of the cyclic prefix. Therefore, this is X0 plus, I am sorry, this is X3, which is the previous symbol to X0 plus V0. All right. So, what we have done is basically, because we have added the cyclic prefix, all right, and the sample X0 has interference from the previous sample, and the previous sample is X3. Therefore, we have H0 times X0 plus H1 times X3 plus V0. Okay. So, that is basically what we have at the output, that is corresponding to Y0. Okay. And similarly, I have Y1. Now, the rest can be written in a straightforward manner. Y1 equal to H0 times X1 plus H1 times the previous sample, that is X0 plus V of 1. Your Y2 equals H0 times X of 2 plus H1 times the previous symbol sample X1 plus V of 2, and Y3 equals H0 X3 plus H1 times the previous sample, that is X3 plus V of 3. And now, these are the samples, and now we said yesterday That is, if you look at y0, that is if you look at y0, y1, y2, y3, that can be basically represented as the circular convolution of the channel filter H with the transmitted samples X plus the noise, and that is the key operation, that is the advantage that this basically this addition of cyclic prefix is giving us. And therefore, we have something that we have seen in an elaborate manner yesterday in great detail is basically the observation that now because of the addition of the cyclic prefix, what I have is y becomes the circular convolution of H with X in the presence of additive noise. So, this is basically nothing but your, this is your circular convolution, and as a result now if you take the FFT, we know in the frequency domain circular convolution in the time domain becomes, in the frequency domain it becomes a multiplication. Therefore, that is the FFT of H times the FFT of X plus the FFT of V, which is basically your noise. And therefore, they have this interesting property because circular convolution in the time is basically multiplication in the frequency or FFT domain. So, once you take the FFT of the samples at the output, basically the action of the channel in the frequency domain basically now can be represented as a simple multiplication. Therefore, the FFT of the output samples Y is basically the FFT equals the FFT of the channel filter H times the FFT of the transmitted samples X plus the FFT of the noise V. And now let us see how you get the FFT, how you take the FFT. Of course, the FFT of Y is basically you have samples y0, y1, y2, y3. So, you take the FFT of these samples. Obviously, we are talking about the n equal to 4 point FFT, where n is the number of subcarriers. So, the size of the FFT is always fixed, that is n equal to 4 point FFT, that is fast Fourier transform, or basically also the DFT. I do not need to mention this, FFT is simply a fast algorithm for the DFT, that is discrete time Fourier transform, and that gives you the symbols across the subcarriers y0, y1, y2, y3, where each YL is basically generated by the FFT of the small y's, that is basically summation k equal to 0, and I am writing the expression for the n point FFT x k e to the power of minus j 2 pi k l divided by n, and substitute n equal to 4. This is basically your k equal to 0 to n minus 1, which is 3, that is x k e to the power of minus j 2 pi k l divided by 4, which is basically equal to, so your y l equals summation k equal to 0 to 3 x k e raised to minus j pi by 2 k l. So, basically this what we are doing here is we are substituting n equal to n is equal to 4, and that is what you are saying is the capital Y's, that capital Y L, that is the received symbol across subcarrier L in the FFT domain, is now given by the 4 point or n equal to 4 point FFT or fast Fourier transform or DFT, discrete Fourier transform of the received output samples y0, y1, y2, y3. So, this is basically what is this YL, this is the received symbol in frequency domain across this is the received symbol across subcarrier L. Similarly, one can do the same thing for, now let us look at, of course, we have to take the FFT of the channel filter. Now, look at that, the channel filter has two channel taps H0, H1, and I have to take the 4-point FFT, therefore, I have to obviously pad with zeros. So, these are basically L channel taps where L equal to 2, I have to pad it with n minus L zeros where n equal to 4, L equal to 2, because basically I have L channel taps and I have to take the n point FFT. So, naturally I have to pad with n minus L 0. So, this is basically the 0 padded FFT. So, padding with n minus L zeros, and now you take the FFT of this to give you capital H0, capital H1, capital H2, capital H3, and these are the coefficients across the subcarriers. These are the coefficients, or you can also say channel coefficients these are the channel coefficients across the subcarriers. And how do we generate them? Naturally, what we do is we have H of L, the coefficient across subcarrier L, equals summation k equal to 0 to L minus 1, k equal to 0. Remember, we only have channel coefficients L channel coefficients from k equal to 0 to L minus 1. So, that is H of L e raised to minus j 2 pi k L divided by n, I am sorry, this is k, which is equal to summation k equal to 0, in this case L equal to 1. So, k equal to 0 to basically L1, that is H of k e raised to minus j 2 pi k L divided by 4, which is basically equal to your summation k equal to 0 to 1 h k e raised to minus j pi by 2 k L. This is your H L. As we said, this H L is basically the channel coefficient or the effective channel coefficient across the Lth subcarrier. All right. So, the capital H L, which is the channel coefficient across subcarrier L in the frequency domain, is given by the FFT of the channel taps in the time domain. Of course, since there are only capital L channel taps and we have to take n point FFT, right, we have to consider the n point FFT, therefore, naturally you have to pad it with n minus L zeros. Okay. And now, let us look at the FFT of the samples x, FFT of the samples x. Now, we want to take the FFT, that is obviously the n point FFT n equal to 4 point FFT, but observe that these are basically given by the IFFT of the symbols. Remember where we started from, we started with x0, x1, x2, x3, and we did the n equal to 4 point IFFT to get the sample. So, these are basically your symbols and these are basically your samples. So, remember the way we started with in this OFDM, we considered the symbols, the capital X's, and we performed the IFFT to get the samples, that is small x's. So, naturally once you do the FFT of the samples, you get back the symbols that are loaded onto the subcarriers, and that is the other important point to keep in mind. So, once you take the FFT, so basically we had the symbols in the frequency domain which were loaded onto the subcarriers, and you consider the IFFT to get the samples. Now, once you take the FFT of these samples, you are back in the frequency domain and you get the symbols that are loaded onto the various subcarriers, and that is basically the important point to keep in mind. So, this basically n equal to 4 point FFT. So, this basically this gives back your x0, x1, x2, x3. These are basically the symbols or the modulated symbols loaded onto the various subcarriers, and that is what you are getting back after you perform the FFT. And naturally, the only remaining thing is the noise. That is also very simple. You have the small v's, which are the noise samples, additive wide Gaussian noise samples in the time domain. You do the n equal to 4 point. Let me write it a little bit more clearly. You do the n equal to 4 point. You do the n equal to 4 point FFT of this, and what you get back is the noise, the capital V's, the noise across each subcarrier, the noise samples across the subcarriers. What are these? These are your noise samples across subcarrier. These are the noise samples across the subcarrier, and of course, we have V of L, which is given by the FFT, that is summation k equal to 0 to n minus 1 small v k, which is the noise sample, e raised to minus j 2 pi k L divided by n. Substitute n equal to 4, and what you have is summation k equal to 0 to 3 small v k e raised to minus j 2 pi k L divided by 4, which is equal to, so V L, your noise across subcarrier L, that is equal to summation k equal to 0 to 3 e raised to minus j 2 pi, or in fact e raised to minus j pi by 2, because this 2 and you have the factor of 2. So, you have pi by 2 k L, and this is basically nothing but your, this is basically your noise sample. This is basically your noise sample for the subcarrier L. And therefore, now you have the frequency domain. Remember, in the frequency domain, we have the FFT of the output y is equal to FFT of the channel h times the FFT of the samples x, which are basically nothing but the symbols loaded onto the subcarriers, plus the FFT, the noise sample across each subcarrier. And therefore, now rewriting it, I have FFT of y equals FFT of the channel filter h product. Remember, this is important to remember, in the frequency domain it is simply a product, because circular convolution becomes the product. Yeah. So, just to repeat the importance of that, in frequency domain is product of the corresponding frequency components across each carrier, basically product across each subcarrier. That is the important aspect, because each subcarrier represents a frequency component, and therefore, across each subcarrier, what do we have? Across, for instance, across Lth subcarrier, and we have, remember, n equal to 4 subcarriers. Across L subcarrier, we have YL equals HL times XL plus VL, and this is the most important result where YL output symbol across subcarrier L HL is basically your, what is HL, which is the channel coefficient across subcarrier L, XL is the symbol loaded onto subcarrier L, and VL naturally VL, not to forget VL is the noise across subcarrier L. So, VL is basically your noise VL is basically the noise across subcarrier L, and therefore, we said the number of subcarriers is basically the same as basically equal to capital N, where N equal to 4, alright. So, number of subcarriers is N equal to 4, which means we have L equal to 0, 1, 2, 3 corresponding to the L equal to 4 subcarriers, and therefore, for each subcarrier what we have y equal to y0 equals h0 times x0 plus v0. This is corresponding to subcarrier L equal to 0, y1 equals h1 times x1 plus v1. This corresponds to subcarrier L equal to 1. Then we have naturally again the same thing, y2 across subcarrier 2, y2 equals h2 x2 plus v2 across subcarrier L equal to 2, and just to finish this I have y3 equals h3 x3 plus v3 across subcarrier L equal to 3. Okay. So, basically now what we have done is we have written down explicitly the relation corresponding to each subcarrier, that is YL equals HL times XL plus VL. Now, if you look at this system, what you can observe is that for each subcarrier the output YL is simply the channel coefficient times the input symbol XL. There is no inter-symbol, there is no inter-symbol interference from the previous symbol on each subcarrier. Therefore, now if you can look at this model, the incredible thing across this about this model, YL equals HL XL plus VL, this is only current symbol, that is current symbol loaded onto subcarrier L, current symbol, and this is your current output across subcarrier L. And therefore, what we have, therefore, there is no inter-symbol interference from the previous subcarrier, no ISI or basically your no inter-symbol interference from previous symbol on each subcarrier. Remember, in the time domain you still have the intersample interference, the time domain the intersample interference is there, but by intelligently working in the frequency domain by adding the cyclic prefix and converting it back into the frequency domain at the receiver, you have eliminated, or one has eliminated, the intersymbol interference in the frequency domain across each subcarrier, and this is the important aspect of OFDM, that is it eliminates the intersymbol interference in the frequency domain. And what is efficient about this? This is efficient because it is based on IFFT and FFT. So, IFFT at the transmitter, FFT at the receiver, and since IFFT and FFT, that is the inverse fast Fourier transform and fast Fourier transform can be performed in a very fast fashion, that is these are efficient algorithms. As a result, the entire OFDM architecture, the entire OFDM system transmission scheme is very efficient, since it does not employ any matrix inversion anywhere. It is simply based on IFFT and FFT, which are fast operations. So, basically to summarize, employing the cyclic prefix, it has been converted into a employing cyclic prefix ISI has been removed in the ISI has been removed in the frequency domain. Further, this is a very efficient, OFDM is very efficient. To highlight that point further, OFDM is very efficient OFDM employs IFFT slash FFT, that is IFFT at the transmitter and FFT at the receiver, which are, and both of these algorithms are very fast and efficient, which are very fast and efficient algorithms. And to note that there is no matrix inversion, no inversion, which is a very, which is adds to the complexity. There is no matrix, inversion in OFDM. And so, basically that is the, so basically if you look at this equation here summarizes OFDM, which is basically it is no ISI across each subcarrier. Each subcarrier is ISI free. There is no ISI across each subcarrier is ISI free, and basically it is a very efficient algorithm, since it is based only on IFFT and FFT, which can be done in a very fast and efficient manner. So, basically what we have done in this module is basically we have completed description of the OFDM system model, which is based on loading the symbols onto the subcarriers, that is basically performing the FFT IFFT operation at the transmitter, followed by addition of the cyclic prefix. That results in a circular convolution at the output of the channel. When you take the FFT of the output, basically what you get is basically in the time domain, in the frequency domain, it is basically can be represented across each subcarrier as the FFT of the channel times the FFT product times the FFT of the samples, which is basically nothing but the symbols plus the FFT of the noise. Therefore, across each subcarrier you have YL equals the channel coefficient HL times the symbol XL loaded onto the subcarrier plus the noise VL, and therefore this transmission across each subcarrier is inter-symbol interference free, and this is done very efficiently by use of the IFFT and FFT algorithms, which makes OFDM an overall very efficient scheme for transmission in modern wireless communication systems. In fact, as we talked about in the previous module, several 4G standards basically such as LTE and modern Wi-Fi standards such as 802.11n, 802.11ac are all based on OFDM. Alright, so we will stop here in this module, and in the next module, subsequent modules, we will look at the estimation aspect of OFDM, that is how do you estimate these channel coefficients in an OFDM system. Alright, so thank you. We will conclude this module here. Thank you very much.